So hello everyone. Today we will take an introduction about MATLAB and Simulink for modeling mechanical systems. Uh, our content for session today, we will go first with the importance of simulation in every system life cycle. After that, we will talk about MATLAB Simulink environment, also the importance of most important blocks in Simulink and modeling mathematical equations on Simulink. Also, we will solve the lab sheet that in Blackboard. So at the first, I want to make this one. Yeah, the importance of simulation. This diagram actually describes the system life cycle. So whatever the system is, it could be a hydraulic system, it could be electrical, it could be mechanical, it could be whatever. So you have a system. This system has a certain inputs and outputs, and you want to model the system. So you will start first with a block model in the loop block. So for example, how can you translate the physical phenomena to such a formula to make some tests on Simulink? So you take a governing equation. If governing equation is okay to describe the system's inputs and outputs, or even state space representation. However, we here focusing on governing equation because we're doing a mechanical. After this step, after you define the model system mathematically, you go in software in the loop implementation. So we have actually several softwares. One of them MATLAB Simulink, LabVIEW. There's another one for ANSYS, but hopefully we will use MATLAB Simulink because it's provided by the university. So after you build your model, build your controller, define your inputs, outputs, and run some simulation software in the loop, you go in a processor in simulation. So you have a system, you design the controller, you model everything, and you want to make this system go in real life implementation. For example, you have a car, you you want to design a suspension system, you model your system, you do some simulation, and you want to run this model in real life car. So how you will do that? You use a microcontroller board or even FPGA board, like processor in the loop, and running your first version of your control and model in this processor in the loop boards. If it works fine, you go for another one called another block hardware in the loop, which you connect all the actuators, uh, everything in the system to test if the system is valid or not. If valid, finger crossed, you go for actual hardware to actual testing. So what we will learn today or where we are. So as I told you, the model in the loop where the system, it could be a hydraulic system like this one, hydraulic system, or even a mechanical system, suspension, or even electrical system, or even a pneumatic system. However, we will discuss this one today, mechanical system, mass, damper, spring. Uh, and today you will learn how to build a model, Simulink model, how to do some software in the loop implementation, your model, how to see responses, how to see system analysis, and so on. So MATLAB is super easy software. It consists of multiple windows. For example, the middle one. Can you please open the MATLAB? Yeah, the window in the middle, the place where you will write your command. And MATLAB, for example, you want to clear, you want to define parameter, you want to define a gain or whatever. You will write your command in the middle window. Also, in the right window, which is the workspace, this is a place where you store your parameters. So, for example, you write a variable called x, and this variable called x equal 5, where you will store it in workspace. I will show you now. It's all right. And the window on the left is current folder where the project folder will be. Okay. So to start the Simulink, you can write in command window a Simulink command, or even you can click on Simulink button there. That clear? So we have, when you just click on this one and create a new model, Yeah, just create a new model. Yes, this one. Up one. Okay, that's right. That's right. Uh, you will see the Simulink environment. Okay, we have here a simulation section where you can define the stop simulation time, the run and stop the simulation as well. And we have here the library browser where the all blocks that you will use it to build your simulation. So I'm gonna go to Simulink here. As I told you, this one is the command window. For example, if I write a Simulink, it will open the Simulink. Or even I just click on Simulink, it will open the Simulink. So just create a blank model. Yeah. So we have here a library browser where this library has all blocks that we will use in our simulation. And also, as I told you here, this window for running the simulation, stopping, put a stop time or whatever. So we will back here. So we have actually some couple of blocks, very most important blocks, which is input blocks. So every system has an input. Every system has an input and output. And for inputs, for example, we have a ramp input, you have a step input, you have sine wave input. So if you can see here in RAM, the signal increase over the time till the end of the simulation. Like you accelerating your car, just putting a high acceleration, car accelerate till the end. Or even you excite the system with a continuous signal. In the step input, we can see here the step you excite the system, okay, but in a fixed point. For example, here it was a 1. So you put your gas acceleration in 1. The system will be run on 1. And sine wave, here you're accelerating, deaccelerating, accelerating, deaccelerating, and so on and so forth. Okay? At this point, it's clear? Yes.
The unit for the input block can be anything.
Yeah, it could be anything. Yeah, sure. Yeah, for example, this could input a current, a voltage, a force. What else inputs we have? Excitation. Could be a noise.
So once it's blended, you have to specify like before while connecting to the
Yes, yes. So how can we visualize the output of the system? We have two blocks actually. One of them is a scope, which is built with which this one is help you to plot your response, and we will see now. And display can display the numbers of the value of the parameters. So as I told you, we are doing model in the loop. So we making a mathematical equations, okay, and taking this mathematical equation in the in the model in the Simulink to do some tests and some simulation on it. So for example, this one a mathematical equation for a first order mass number spring. A normal first order mass number spring. We have here acceleration 1 over m f, which is the force, okay, kx, which is the kx is a spring, and b is a number. Super simple equation. So how can we model something like that? How can we which actually the blocks that we can use it to model this equation like that? This one is super simple. You might have two equations for 2 degrees of freedom. How can you connect them? We will see now. So, for example, if we can see here, actually we have a parameters. We have a parameters and gains, and there is big difference between parameters and gains. Can anyone know what the difference between parameters and gains? Okay, the parameter is something changing over the time. For example, I'm talking about here acceleration. Acceleration changes over the time, the displacement changing over the time. the accelerator, for example, the speed or the velocity changing over the time. However, the gain does something doesn't change. For example, if the system moving with a mass, can the mass change? No. So we model the mass, the stiffness of the spring and the number in again something that doesn't change with all the time. If and only if the system, the x parameter changing over the time, this is another story. But we are here talking about super simple system consists of parameters and gains, and we can model the gains, which is k and b and 1 over m in a game block. You can see this one here, a game block. This one. This one is a game block. This one is a game block with k, and this one is a game block with b. And the key with its x, we can sense it. So if we want to capturing the sensing of the x, for example, the velocity, for acceleration, whatever, what we will do, we will use output blocks, which is called displacement. This is something changing over the time. We want to know, oh my God, how this acceleration changing over the time. For example, acceleration in 5 seconds, 10 seconds, and so on and so forth, and or the display. So this one is the most simple thing. So in terms of integration, so we have a block and we want to have an input, for example, acceleration. We are inputting acceleration. I want to see how can I bring the acceleration? How can I take the velocity? How can I know the velocity or even the displacement from the acceleration? We can do some integration, and there is an integration block, okay, in Simulink. Life is super easy in Simulink. You don't need to do anything. Just putting your blocks and that's it. For example, this one is 1 over s is integration. If you can see here in the left, x dot dot, which is acceleration. We integrate the acceleration 1 over s till it become x dot for the velocity. We do velocity. We do another integration for the velocity. We come up with a displacement, and we can visualize them, okay, where in scope or even display. I'm gonna show you now how to do it. It's super easy. So can I ask everybody to go to Blackboard Shell, Learning Material Dynamics Week 9, and read just the PDF. I will give you just 3 minutes or 4 minutes. Just read the PDF. So guys, today we have three aims for this session. We want to do three experiments. The first one, we want to simulate the undamped vibration simulation, the undamped system without damper. System consists of mass and spring only. And we want to do a damped decrement vibration simulation, the system with a mass damper spring. Also, we want to study uh, the variation of damper on the system. When we increase the damper, what will happen? When we decrease the damper, what will happen? Also, we want to do 2 degrees of freedom, hopefully, today. So I will do the first one. After that, I will help you to do both of them. So we can go here. Yeah. So take care, because at the end of the first experiment, we need to uh, fill this table. We have a given data, we have a required data. So we're working towards this data. So in terms of data, before you start any simulation, before you start anything, you have to define your data. So how can you define your data in MATLAB? You can go to MATLAB and you can create a new script and can name it as a data. For example, what we have mass and damper and spring. We can say the mass m equal. We can go there here man 1 equal m equal 1 kilogram. We can write 1 uh, kg. We have equal k equal 20 Newton meter, 120 initial displacement and initial velocity 2. So we don't have damper, so damper will be d equal 0 for now. This one will be Newton over meter, so on. Okay, so if you just run this, as I told you, we defined our data. So where we can store it? We will store it in workspace. If you just run this script, what will happen here? We have a mass and k-spring and damper values. Those values are stored in workspace. So go to Simulink. We can save this one as a lab. So we are talking about a system, okay, with no dampers. We can put the system like here. So guys, do you mean if we have a suspension system without damper, what will be look like? Will be look like will be look like that. This guy actually can. This car was working without damper. It's shaking. Look, there's no damping. So this our system that we will be model. Oh, thank you. We will go back to you again later. So as I told you, we starting to define. We can also so take this one copy. Yeah. So this one is a mathematical equation that describe our system, but we don't have numbers, so we will cancel this term, which is x. They will put here x. I don't know how can I do it or not. However, can I crop? Copy image based format properties, convert to marker. Marker. Anyway, we will model the system without any number. So how can we will from where we will start?
Sorry.
We will yes.
How do we import
This one. This one. Just drag it and throw it. And you can search on Google mass number system. You will can download it. And also this one should be on the Blackboard. Hopefully today at night should be all those data on the Blackboard and video as well. Okay, but just follow up with me. Also, you can take it here, for example. Look this one. Can make a screenshot like that. Copy. Come on. And paste. And that's it. Okay. So we will start with the force. Okay. Here, the force could be anything. Could be sine wave, could be step, could be a ramp, whatever. But we will start with sine wave. So sine wave actually simulating a system where if it moving on like a road. Okay, like the video that I show you. So we have two options to import the blocks. First one, we can go here to write sine. Where is the sine block? Sine, yeah, not, yeah, sine wave. Or we can just write here. We can double click on the anywhere and write sine wave, enter, and it will come. Okay. So just look again to this mathematical equation. What we have here, we have acceleration, and the acceleration equal 1 over m, and I told you 1 over m mean again. So 1 over m again, and force is okay. We import force here, and we have a k, which is the spring. And if you see from f and k, there is a negative sign. So how can we model the negative sign? It's super easy. You can sum, not this one. Yeah, or subtract. So we have here a subtract block. Okay, so what the input is f. Okay, and we have the 1 over m is a gain. So we'll write again, and the first gain we will call it 1 over m. Yeah, this one m in the workspace. What else we have? What else we have in this system? K. So how can we will multiply the k by the x? So we need now to come up with the k with the x. We have x dot dot. We want to get the x. We have x dot dot, and we want to come up with x with the displacement. And if you can see here, the k of x negative f negative the force. So we have a k. So let me bring the k, the gain. And this gain, we will call it k. Oh, come on. Yeah, this k. So as I told you, we have here 1 over m. We have here x dot dot. Come on. x dot dot is multiplied by 1 over m. If you just put this over m in another side, you will see x dot dot is multiplied by m. Is it clear? So we have x dot dot multiplied by m. When we want to come up with the we want to come up with the x, so we will do some integration. So we can write here in integrator. Come on, yeah. This integrator, we will go here. So after the integrator, what we will have x dot, but we still need only the x to multiply it by the k. So we will bring another integrator. So will give us the k, the x. So here, x dot dot, x dot dot, x dot, and this one is x. So we will flip this one because I told you the force negative k. What does it mean? The force, which is sine wave, force sign is positive, and the k is negative. So we will flip this one another side from this one. I want to flip it. Oh, come on, MATLAB. Control I. Oh my God. Control. Let me see. Control. Oh my God. This guy is hacker. So, so we will. Come on. Yes. Any question? Yeah, yeah. Yeah. Just you have to define your parameters. Yeah. Yeah. From MATLAB script. Yeah. Like I show you. Yeah. Just create a MATLAB file and just save it. Save it. Yeah, guys. I'm here. Yeah. Any problems? Model. Yes, this one. Yeah. Yeah. Yes. X dot dot. Yes. Yeah. Yeah. This one. Acceleration. Yeah. Be multiplied by 1 over m. Why? Yeah. Actually, the real x dot dot was multiplied by m, but we divided by 1 over m, so we put 1 over m the next side of the equation. That's why I'm going to tell you x dot dot 1 over m. Okay? Integrate the x dot dot to be to be x dot. X, yes, yes. To k to multiply x by k. M is a force. Sine wave. Yeah, we can arrange, but I'm looking for a pen. But I didn't have a pen in the board. A K is spring. Yeah. Yeah. Should be M. Yeah. The 1 over x dot dot equal 1 over m. So we multiply by 1 over m to get x dot dot. We have two sides to the equation. Okay. X dot dot on one side and x dot dot, what x dot dot equal 1 over m first negative 3x. Yes. Yeah, because we have when we over Yeah, this one x equal kx equal. Did you? Yeah, you can take a screenshot. I can take a screenshot. Yes. One over n. Yeah, go here. Actually, you want to know space? What workspace? One minute. You start. How to correct a control save? How to save the file? Yes, write it data. Write save. Kilogram. Kg. Also we have a K. K equal the K value. Let me check the K value. What? Say you have to find again. One yes. That's fine, no problem. Yeah, with this relation, was like that. It's a big polygram. We have here force. We have here oh, sorry. We have here force, pulley. We have here a case. Okay. So we taking first Newton law, which is F equals zero, or F equals zero the problem. We have X double dot M, negative this one is M, this one is M, this is positive side, and this one is positive natural side. Small. So we putting the F M sorry, we leave the X double dots. Let me show it here. X double dot is equal. Put the one here. It will be S, which is a positive. This kx will be negative because will be on the other side. Will be kx all m will be multiplied over m. If you look at the we start from the right to the left, we have 1 over m, okay, and here x double dot. So when we try to model it, we have a positive negative model. First block will be again, this is 1 over m, this one. Okay, we have a force. Force will be the input with the sine wave. It could be still, it could be round, it could be whatever. 1 over m. And we have here x double dot. Okay, x double dot will be, we will integrate 1 over s will be x dot. After that, we will take, we will integrate it one more time. 1 over s, it will be x. This x actually multiplied with k, and we have here positive for the positive value with the f, and negative for the negative value with the k. And we will go back Super easy. Guys, guys, guys. So, guys, just a minute in here, and I just want to finish this one. After that, I will go everyone to see what the problem, to sort all the problem. So we have here our model. We want to see the output, which is x. We want to see the x dot dot. Let me write here. We want to see the x dot dot response. We want to see x dot, and we want to see the x, the displacement. What we will do here, we just scope and take this one. This one we can displacement. We can write another scope here for velocity, and we have another one here. Scan your card. Scan your card. Scope for acceleration. We can put it here or there or whatever. We can not here, this one actually. So we run our model. If we can check on displacement. Yeah. So we have here the sine wave that coming from the side. Let me show you a trick. Let us compare the actual output. So the sine wave, if you look at here, the sine wave with amplitude was equal 1, look like that. But after the system, because it doesn't have any number to damp the frequency or to make it a good shape, so it starts to a rough response like that. Let us check, we validated if it's correct or not. We don't have the response here. However, also there is initial velocity. We need to put initial velocity to 2 meter second, and initial displacement 0.2 milliseconds. So we have to back here. So if you want to know how to can make initial velocity or initial displacement, double click on the first integrator and put the initial velocity by 2. Yeah, guys, double click on the first integrator. Yeah, initial conditions, and put a 2. And the second integrator 0.2. Initial value 2, and the second one will be 0.2. Oh my god. 0.2. Okay, run. Yeah, that becomes more clear. Let us try another input, another fourth step. For example, click run. If you see here, guys, the step response look like that, and the response, actual response of the system is like damn, like that video you show. The car was shaking up, down, up, down, up, down, up, down. However, he's putting an acceleration like a fixed point acceleration, just a 10. But however, the response is shaking up and down, up and down. And this is the power of simulation. So you design your system, you model your system, design the controller, you do everything, and you see if it will work or not. If we just take this system and we go in a real hardware implementation and implement it, it will give us the same as this one. It will be shaking. Like the video I will show you. Any question, any comments that anybody finish this one, just do it. Yeah. Do it. what you have here, what you can, you have here to define, need to define the parameter. Yeah, but you have to run to store your data. So the modifier, let's please, yeah, come on, MATLAB desktop utility. We can name this one as lab1, lab, lab. Yeah, so when we see run, where we our one K and M with workspace that I told you, we can go there, double click, M, here, click apply. Here we go. Run. So if you want to add K, so we can put a game. This game we can name it K. Like to name it. Where is the game? A small game. Apply. Okay. We can also add the data function. 1 over S, 1 over S, and give displacement. This one is to go to library browser. Yeah, this one sign, but this one called some. You can do it together. Here, some. Yeah. Yeah, we have a first real on one for the kilogram, and A for community, and the initial displacement 0.2, initial versus few, and you have to calculate the omega, which is omega was equal K over M. What the K value equal? The K value. Just give me 1 second. I will give that to you. Just look at me, guys. Guys, can anyone just 1 minute attention here? Yeah, if you can look at here, we have here actually a table. We want to fill it for a first real that we did it. We made the initial displacement, the initial velocity. We have to calculate the omega, which is k over m, k over m or m over k. Yeah, that's perfect. So we want to calculate k over m. Also, we want to take the maximum displacement from the graph, and the maximum velocity from the graph, and the maximum acceleration from the graph. How can we do that? I will do for the first trial only. Okay, so we can go back. What the maximum this amplitude was 0.5, about 0.5. So maximum amplitude, this 0.5 as amplitude. And maximum velocity was about 2.1, 2.1, 2.1 amplitude. And acceleration was 10. Oh my God. 10. Is it clear, guys? Yes. I'm coming. We have here add and subtract. We have no subtract. Yes, I'm coming. Just start step will make it perfect. We are waiting for the sign. Just include the sign for now because sign is not clear. Yeah, but I want you to do it in step response. Much easier. Just click here. There's delete. I will make that step. the input and the output of the system, you can take a line from the input, which is step, and put it in the displacement block in scope. So it will, you have something look like that. This one is the input, and this one is the output. Okay? Guys, because most of you are confused at this point, this one is very important point. Yeah, can everyone just look at me? Uh, your friends asking me why we putting 1/n here. Okay? So what's the story? If you look at here, guys, we have an governing equation x dot mx dot plus key x equal f. We just made x dot f like the equation like we saw here. We key x we put it in another side, which will be mx dot equal f negative kx. Okay. We after that we will divide 1/m in another term. So how can we that we have two equations? We have equation, we have a bracket here, this bracket that contains f negative kx multiplied by 1/m. We want to shape the first bracket. How can we do that? We have f, which is step input. We did f step input. We added a subtract a block, which will be subtract the f, the input negative kx. What else we have to shape the x dot dot? We need 1/m. So if we multiply this bracket that contains f negative kx by 1/m, we can come up with x dot dot. Did you get it? Come. If negative kx is a bracket, if we multiply it by 1/m, we can come up with x dot dot. Did you get it? Seriously? Seriously? Yes. So actually, guys, just please look at me here, please. This one. Look at the blackboard, the board. If this one step is if, and this one k. If positive negative k x, which is this one. This is a bracket. If we multiply this bracket 1/m, just like this one, we can come up with x dot dot. X dot dot. If we multiply f negative kx by 1/m, we can come up with with x dot dot. Again, x dot dot, and we want to again, guys, because we will go in a second order and will be much complex. If we multiply this bracket, that f negative kx, if negative kx by 1/m, we can come up with x dot dot. Is it clear? Are you sure? Everyone happy? Yeah, take this one. And thank you for letting me know. Yeah, let's do it. Yeah, did you finish? Any problems? Any comments? Yes. Yeah. You want to connect this one displacement? Yeah. Yeah, I'm trying to. Oh my God, brother, how can you? You have mouse because I want to look how I made it. Yeah, look how I made it. I just click look with right click on here. Guys, just we will go. The second part, guys. We want to run that second experiment. Guys, we want to run that second. Any comments, any problems in the first part? So we want to run the second experiment, okay, which we will have a damper in the system. So the first one was the damper without damping. Second one will be we will add a damper in the system, and we have here second experiment. Let me show you the table. So actually, the second experiment shaped the suspension system in the car. The suspension system in the car had a spring and mass, which is the tire, and which is the tire, and the damper. So we will add the damper on our system. Okay. So how can we do that? We will first go to Simulink at the same one. We will insert that. We have here a mass and force and K and damper. So again, guys, because there is someone was asking about this bracket. So we have two sides. We have a bracket which is contain F negative Kx negative Bx dot and 1 over M. So first of all, we will shape this bracket. How can we will shape it? We will write here a step, for example, a step which is a force. Okay, we have a step. So we need a sum block to add a negative and positive side. So we will use add block or even a subtract. So we have here only two inputs. We want yes.
Yeah, it's both negative, right? Minus 10 minus this tan cos. So we have to use a subtract block, right?
In the last example, we had a lot to use subtract.
Yeah.
But in this one, we have to use a plus and subtract. Why? The first one is a plus for a K, for the F, negative and negative. Okay, so how can we add another input? We can double click and write positive, negative, negative. There we go. So we will connect. What we will connect? We will connect the positive, the positive, which is a step, it's a force first. So what we need else? We need the K and we need the B with a number. Where we come from? We just bring again for the K. Yeah. And control I. And we need also the B. Control I. D. Oh, actually D. It's not a B. So we have here a B and a K and D. Okay. So what we need else? We need to come up with the x dot dot. How can we get x dot dot to bring x dot and x? We multiply 1 over m. So we will add another gain. And we call it 1 over m. So if we just connect this block or multiply 1 over m by what, we will come up with x dot dot. So we need integrator. We need one more integrator. So if you look at here, guys, we have here x dot dot. X dot dot. It come in the integrator, got out x dot. One more time will be x only. So what I want from here for at the first, if you look at here, guys, we have b x dot. So we will take x dot to b, and we have x. We will take x. So today, and I want to see the response. What should I will do? I will bring a scope. Here. Is that funny? Yeah. So we have what we have here today. What we have D and B and K. We will connect this one here. This will connect this one here. So again, first we will shape the bracket. Where the bracket? What's this bracket consist of? We consist of f negative key x negative key negative bx dot. So this one is f, which is step input, negative the d negative dx dot, which is coming from here, and negative k with x, which is coming from there. So after that, if we multiply this bracket by 1 over m, what we will get? X dot dot. Is that clear? Run. Hopefully it can run. Yeah, to run. Yeah. So actually we didn't because here actually, guys, I made the number with 0, but I will increase the number now to where we have, yeah, the number will be 1. Let us try. We have the same initial displacement, initial displacement and initial velocity. So we have initial, we will go workspace, we'll change this one to 1, click run to update the list, and go back and click run. Yeah, look at here, guys. The system start to damp, but at the end it will be damped because the damper come up to damp the system down. Okay, let's go do it. Yeah. Number, look at the table. The number was 1. Yeah. Click run to update the list. Yes, this one is perfect. Yeah. This one is I will start with this. Right now, so velocity. Like this, yeah. This. Or the end value. This one giving end value. Yeah, yeah, you can add. Yes, yes. Yeah, you can click, double click here, drag across. Go. Che sì, which is the activity one. Just bring some water. That will be. So guys, everyone finish the second degree of freedom. Yes, yes. So guys, just I'm asking everyone finish the second part. Yes. Guys, if you want to know more data about the simulation result, you can go here, right click. So you have here the maximum, the minimum, the peak to time, the mean, the median, the RMS, the time. Okay, yes. Yes. Guys, so we have here a system, okay, for a quarter car model physical system with 2 degrees of freedom. So we have two masses, two springs, one damper, and they have a surface changing over the time. And we want to simulate this system in Simulink. Okay, so actually, since it has two masses, that means it has two degree of freedoms, two equations. For example, the first equation for the first mass, which is m1 x dot dot equal f, which is a force that coming from down, equal negative k x1 negative x2 negative b1 x1 dot x dot 2. You know how to do this. You know how to come up from to get this equation from modeling the system, from discovering equation. Is it clear? Huh? These equations in the literature, uh, modeling the system. Two equations, one for first mass, which one m1 equal x dot dot equal f, which is f here to the damn the system, to control the system. Negative k x k k1, which is k1 negative, this one a displacement, and this one a displacement, k1 negative k2 multiplied by k1 sorry, x1 negative x2 multiplied by x1, and also the b1, this one b1 negative negative x1 dot negative x2 2 dot. So we come up with this equation for the first mass. For second mass, we have here a force which is F positive Z, which is the external amplitude, the root of the root. Okay, so we consider it as a force because it input over the time. So we have here the m2 multiplied by the x2 dot, like here, equal negative f, okay, plus z, negative f, okay, negative f, the other side, plus z. So actually the rule of this f, this force, is to control this. For example, m1 is a car chassis, the car body, and m2 is a tire. So, and we have here actuator to control the tire, which doesn't affect the car with the extended speed. For example, the driving car, like some ups and downs in the road, to damp the system. So we actually have this negative f plus Z to damp the Z of the road to make the car steady, moving in a steady state. And we have K1 because it's K1 connected to the tire, the M2. So it appears here in the equation. So K1 equal X1 amplitude negative X2 because they have a relationship between each other. The car body and the tire had a relationship between them. Okay, which is displacement x1 and x2 acceleration. If the tire accelerated, the obviously the car will be dampened as well. But hopefully we have this force to neglect the effect of the z. Okay, we have plus p1. Where is p1? Oh, p1, this one, because it's connected to the tire as well, so it appear in the second equation, equal x1 dot negative x2 dot, and we have x2 negative x2 plus x2 k2 x2. So how can we model something like that? Okay, in Simulink. Is it hard or easy? It's super easy. So we have two masses here. Go to the script, define the parameters as I told you. The script, we have a first mass, let it the m as it is, and define another variable called m2. Again, guys, we have here another k, which k1 and k2. We will go to the script, the MATLAB script. For example, we will write m2 equal, for example, what we have here, and the table we can shape it in a good way. M1 M1 was 290 kilogram, and M2 equal M2 equal 12. Guys, if you just look at here, please, M1, as I told you, M1 is a car mass with about 290. For example, we have a car with a mass 1 ton. Okay, the quarter 190, about 190, and the tire and the suspension equal 12 kilograms. So that makes sense. A 12 kilo for the tire and 290 for the mass, a big mass. Oops. Okay, what else we have? The K1, the K1 was 1618, and the K2 equal, well, K1, K2, 1900. And also we have B15, let us say T equal 1500. Yeah, does it make sense?
And there are two values for
Well, for the M.
no, no, D1.
Oh, D1, we can see D, yeah, D1, for example. So this one is the second system. We can write a comment. X stream to DOF. Is that clear, guys? Does everyone made this step? Yeah. We have two masses. First mass for the car, which is 290, a big car. For example, 1 ton. We study 1/4 for it. So this one approximately 290 kilogram, and we have a small tire about 12 kilogram, and both of them are connected to each other, making a 2 degree of freedom system. Okay. P1 and P2 and P1. Is it clear? Definition is finished. Is it okay? Guys, so back to Simulink. As I told you, we have two equations with a lot of parameters. So from where we can start? From the right side, that contain if is the input, negative k1 and k1, and this is this bracket, and b1 with the second bracket, and we have also here the second mass. So we have two systems in one system. How can we do that? First of all, we can import the step. Uh, me. This one is a force. And we also how we need an add block, subtract 1, 2. So subtract block, and the force is positive. So we will put the force in positive, and we have to negative. We will make this one a bigger a little bit. So we have positive, and we want to multiply. We want to come up with x dot dot. Yes, we want to come up with x1 dot dot. So what we will do? We will import a gain. This gain will be 1 over m1. Yeah, I didn't run it. Just wait a minute. M1. So we have M1 here, and we have two integrators. So why we will bring two integrators to bring x dot and x. So one integrator. So we also need a K1 and B1, which is gain. So we will put another two gains. We will name the first one, for example, K1. K1, and second one be D1. Yes. As I told you here, x dot dot, and here x dot, and we have here our x. So we have here x will be there, and x dot will be here. We have displacement. So guys, if you look at here, we still need two gains. If you look at here, for example, I connect this one here, and I connect the B1 here. And if you look at to the equation, there is another term. So kx1 is okay, because this one kx1. Let me what k. This one kx1. Yeah, this one kx1. So okay, and this one 1 and 1. Also, this one will be a constant because the force is constant. Constant with 40, 45. Okay, guys, but actually we still need to add kx, k2, k1 x2, and we still need to add b1 x2. So from where we can come up with x2 and x2 second equation? Yeah, so we will come up here. We will look at second equation here. So we have more two terms, and two terms are negative, negative, but will be positive, and negative, negative will be positive. So we have two negative, negative because x1, q1 will be negative, and we have two of them are positive. So we have actually one more gain, two more gain, and the first gain will be k1, and second gain will be d1. Control I, control I. So for now, this one need to be multiplied by x2, x2 dot, and the k1 need to be multiplied by x dot. So we will share the second equation. So we will go here. What the input in the equation? Negative z, okay, plus k2 z, which z is a sine wave, like the root, simulating the root. And what we else we have? We have here negative k, okay, no problem, and plus k2z, that's okay. This one will be multiplied by k. Negative k1 x1, okay. So we will subtract. Can you guys finish the first part first? This one, can you finish it? Yeah, just work on it. Guys, look at here. Here more clear. Just 45 constant force. We have subtract. We following this equation that the same as on your lab. We have 1 over m will give us x dot dot 1 over s 1 over s. We have our four gains. Both of them are multiplied by x 1 dot. and both of them we will multiply them by x2 dot and x1 dot x2 dot as well and x2 dot x dot x2 and x2 dot. So how many terms we have here? One, two. Let us say the positive first. Negative will be negative. After that, positive. After that, k1 will be negative. After that will be positive. After that will be positive. Negative, negative. So guys, we will start again. So we have here negative f, negative f. Where is the f? This one is the f, the force. We will take right click from on this line. Oh, force. What we have here z, which is a sine wave. We put it like here, positive. So we have negative f, positive f, and also we have negative k1, negative k1 x1. So negative k1 k1 x1. We will take a line from here. And if you look at here again, k1 k1 x2 positive. So we need to add 1 over m 1 over m2. Come on. m2 and say apply. Click apply. So we have here add more two integrators. One more integrator. So we have here x2 dot dot and here x dot x dot x dot dot x dot. We have here x2 So guys, if you notice if you notice here, we need x1, x1, k1, k1 positive x2. So where we come up from here, which is x2 connected, and also we have x2 dot positive x2 dot in the first equation. So what we will do? Oh, that easy, super easy. So we want to finish scope. So the second mass for yes.
It's correct to the plus, right, on top for the first one.
First
This K1,
K1.
K1, V2 and V1, this,
Yeah.
yeah, sorry, K1 H2 and V1 H dot 2. Both are correct to the plus.
Yes, because
For
of
the
negative by negative
okay.
equal positive.
Okay, okay.
Yeah, that's why we made it positive. I will add again here the gain, another gain, which is K2 and B2. No, we don't have B2. Uh, we have K1 as well. K1. K1 it's okay. We need here K2. K2 apply B1. We still have B1. Yeah, we don't need it. We need B to B1. D. I name it D1. Control I. Control I. So again, so where we are here, where x1 x1 k1 negative k1 x1, and we need to multiply k1 x2 k, which is plus. We'll add here another gain. Control I, and we will name it K1. No, no, because it's K1 connected to K2 to X1, but here we need K1 X2. No, you can't, because actually K1 on the top multiplied by X1. I need K2 multiplied by KX1. That's right. K2. So I need K1 X2 X2 X. Oh, nope. Come on. Done. K1 X2. So this term is done. This term is done. We have this term B1 P1 X1 dot P D1 X1 B. Yeah, will be positive because B1 X1 is positive, and we need one more D. So what else we have? K2 K2 X2 K2 to X2, and we done. But we have to run the simulation for an instruction, because there is some kind of instruction here. Yeah, the Simulink of the equation 4 is described in the figure. Simulation. So simulation time. If you look at here, guys, simulation time is 5 seconds. The sine wave amplitude is 1, and the constant force 45. So we can 5 seconds here, and the sine wave amplitude is 1. What else we have? The constant force, simulation 5 seconds, and let us see. Yeah, if you look at here, because the force is let me input give the input and compare between them. If you look at here, guys, the big curve is the sine wave, which is the root. Okay, thanks to for the controller and the for dampers that can make this input in output look like that. It's dampened in the root. Is it clear? Yeah, yeah, guys, come on, do it. Also, guys, you have to finish this table. You have to, after you plot the Simulink, you have to put it here and there, so on and so forth. Okay? Yeah, because you define the initial conditions. We don't need to, yeah, if you want, yes, and simulation time at 5 seconds, just click run. Oh my god, yeah, sign, yeah, check the equation again. But it's quite easy, don't worry. Yeah. Anyway, those should be available on Blackboard. They must be available on Blackboard, so. So I will stop the recording. Hopefully this record should be available on Blackboard at the night. So